Stand inside Hagia Sophia for a moment and look up, because what you are seeing should feel impossible. A vast dome of brick and mortar, hanging above an open space, in a city that has spent centuries shaking beneath it. And yet it is still here. Not because the problem was simple, and not because the building was perfect. In fact, part of the answer lies in something that failed. And once you see it, you will never look at this dome the same way again.
More than 1,400 years, people have stood inside Hagia Sophia and looked up at the same impossible question. How is that dome still there? It is not just large or beautiful or old. Strip away the mosaics, the marble and the light, and what remains is an engineering problem. A vast masonry dome raised high above an enormous open interior, built in the 6th century in a city repeatedly shaken by earthquakes. By every obvious rule, this should be difficult. So what is actually holding it up?
Before we can understand how this structure survives, we need to understand the danger hidden inside its shape. From below, a dome looks calm.
But masonry does not simply sit still under its own weight. The forces begin to travel. And as they move, the structure starts trying to do something deeply dangerous.
It does not only press down, it tries to spread.
To understand the problem, forget Hagia Sophia for a moment. Imagine a simple masonry dome. Every brick has weight. Gravity pulls that weight downward. But because the bricks are arranged along a curve, the force does not travel straight down. It follows the shape of the dome. Part of the load moves downward, and part of it pushes outward. That outward push is called thrust. The wider and flatter the dome becomes, the harder its base tries to spread, and that creates a dangerous problem. Because masonry is very good at being squeezed, but it is far less comfortable being pulled apart.
Ancient engineers already knew one reliable way to control a dome. Make the support obvious, make it massive, make it continuous. That is exactly why Hagia Sophia is so strange, because when you compare it to the simpler Roman solution, the reassuring logic begins to disappear, and the real mystery finally comes into view.
There is a simple way to deal with that outward thrust. Support the dome continuously. Look at the Pantheon in Rome. Its dome sits on a massive circular drum. Think of it as an enormous stone ring beneath the dome. As the dome presses down and tries to spread outward, that thick circular wall supports it all the way around. The load has a continuous path into the structure below. It is massive. It is heavy. But structurally, the idea is easy to understand. A circular dome resting on a circular wall. Then you look at Hagia Sophia, and that reassuring ring is gone.
So if the space below the dome is not a solid circular wall, then the weight has to be caught, redirected, concentrated. What looks like beauty and openness is actually a hidden structural machine. And once that mechanism is revealed, the building stops looking magical.
At Hagia Sophia, the support is not everywhere. It is concentrated. Strip away the marble and decoration, and the structure begins to reveal something extraordinary. The enormous dome is organized around 4 major supports. 4. Between them are vast openings, arches, and empty space. So imagine removing most of the circular wall beneath a masonry dome and leaving only a few massive support zones. The weight has not disappeared. The outward thrust has not disappeared. But the continuous path into the ground has. Somehow, those forces must be gathered, turned, and guided toward 4 specific parts of the building. How do you make a round dome do that?
It sounds simple until you try to draw it. Take a circle. Now, place it over a square. The circle touches the square in some places, but look at the corners. They do not meet the dome. There is no continuous wall beneath the circular edge, and that means the load cannot simply travel straight into the structure below. At the scale of a small roof, this is a difficult geometry problem. At the scale of Hagia Sophia, it becomes dangerous. Because in a building, geometry is never just a shape. Every curve creates a path for force, and if that path ends in the wrong place, the structure begins to move.
And Hagia Sophia's builders made that problem enormous. They were not trying to cover a small room. They wanted a vast interior, open beneath a single dominating dome. But every meter of open space creates a trade-off. More open space means fewer supports. Fewer supports mean the weight must travel farther. And when that weight finally reaches a support, more of it arrives at the same place. The load becomes concentrated. So that made Hagia Sophia breathtaking also made it dangerous. The builders were removing the supports that would have made their job easier, and somehow they still intended to place a massive dome above it. This was not simply an architectural challenge, it was an engineering gamble, and two men were asked to make it work. Anthemius of Tralles and Isidore of Miletus. They were not known only as builders. Their work was connected to mathematics, geometry, and physical reasoning, and that matters. Because Hagia Sophia does not look like a structure solved by simply adding more stone. It looks like a structure built around an idea. Use shape to control force. Guide the weight instead of merely resisting it. But there was one problem. An idea that works on paper still has to survive gravity. Now imagine that force at the scale of Hagia Sophia. A vast dome pushing outward, but instead of a continuous circular wall resisting it, the forces must pass through a far more open support system. That changes the way you see the building. It no longer looks like a massive object simply resting on the ground. It looks like a balancing act, because if the supports move, even slightly, the shape above them changes, and when geometry changes, force finds a new path. So perhaps the question is no longer how Hagia Sophia was built. Perhaps the real question is, how close did it come to failing? And there are clues, if you know where to look. The Hagia Sophia we see today is not perfectly regular. It is not an ideal geometry preserved untouched for 14 centuries. Look closely, and the building begins to tell a different story. Signs of movement, signs of correction, signs that the forces inside it were not always under perfect control. The great supports do not tell a story of effortless stability. They hint at strain, at adjustment, at a structure responding to problems its builders could not ignore. And suddenly, Hagia Sophia stops looking like a perfect answer. It starts looking like something that had to be learned. And that changes the mystery completely. Because once you stop looking at Hagia Sophia as a miracle and start looking at it as an experiment, a new possibility appears. What if this was not a perfect solution discovered in one brilliant moment? What if the builders did not solve the problem the first time? What if the dome that made Hagia Sophia extraordinary was also the part that exposed its greatest weakness? Because hidden behind the structure we see today is one detail that changes the entire story. The first great dome of Hagia Sophia did not remain standing. It came down. But why? Was it the earthquakes, the materials, the enormous weight above? Or was the real problem hidden in something far simpler, the shape of the dome itself? Because when we reconstruct the first dome of Hagia Sophia, one detail changes the entire force system, and it begins with a question. What happens when a dome is too shallow? In the next chapter, we follow the forces that pushed Hagia Sophia toward disaster and uncover the mistake hidden in its original geometry. If you want to see how one small change in shape can decide whether a building stands or comes down, subscribe, because this investigation has only just begun.